Hello and welcome to the Thermodynamics Part 4 podcast. We'll be talking about the applications of applying the values, or at least the signs of delta H and the signs of delta S, or enthalpy and our entropy, to delta G. And we're going to see if reactions are temperature dependent or not. In previous podcasts, so podcast number 3, I explained delta G. In podcast number 1, I explained enthalpy. And in number 2, I explained entropy. So go back and watch those if you're confused about any individual aspect of this. So what we're going to be doing today is we're going to be putting all of them together. So we're going to be looking at whether the sign and the value of delta H and the sign and the value of delta S how it's going to impact delta H, and whether the reaction is going to be temperature dependent or not. So we know that if we have a negative delta G, the reaction is product favored, and a positive delta G will be reactant favored. Those reactions tend not to happen, or if they do happen, they're going to tend to stay mostly as reactants. So when we talk about these type of reactions, we're going to talk about driving forces. So is delta H going to help get a negative delta G, or is delta S? So the two possible driving forces are going to be a negative delta H and a positive delta S. And if you look at this reaction just algebraically, it makes sense, because if you have a negative delta H, that's going to contribute to a negative delta G. And if you have a positive delta S, it's minus a positive. So the overall factor here is going to be negative. So you're going to have a negative value that can help contribute to a negative delta G. So we're going to go through 4 examples, and we're going to look at cases where they're not temperature dependent. It's always a negative delta G. It's always a positive delta G. Or you can have one that is temperature dependent at high temperatures or low temperatures. The one thing I want to mention is you can actually calculate the values of delta G, delta H, and delta S. We're not doing that in this podcast. I explained that in the individual ones, but all you would have to do is just take the sum of the products minus the sum of the reactants. So for any of these, so if you're going to a table of delta S values, a table of delta H values, or a table of delta G values, you can just do the products minus the reactants. And we've seen lots of problems like that in the sample AP questions. One of the other things I want to note here is, see these little circles up here? That means that the reaction is under standard conditions, which is 25 degrees Celsius. That's different than STP for gases, because that would be at 0. 1 atmosphere of pressure, so that is the same. And more specifically for this, it's 1 molar. So all of your reactants and all of your products are 1 molar, which is very unrealistic, because in a lot of reactions, we're not going to have exactly 1 molar solutions of everything. And how do you know you're going to make exactly 1 molar products of everything? So there's actually a correction equation that allows you to calculate the true delta G value from the delta G standard. And the only time this is really, really important is with equilibrium, and that'll be in the 5th podcast. So if you want to learn a little bit more about that, you can watch that podcast. That's the next one. But for right now, we're going to deal with the standard values. And for the signs, most of the time, it's not going to have an impact, the difference between them. We'll talk about some cases where it does later on. So let's take a look at our first reaction here. This is a combustion reaction between propane, C3H8, and oxygen gas. So the C3H8 is a gas, and the oxygen's a gas. So that would be 6 moles of gas on this side. And we've got 7 moles if we add this up. Gas on this side, so gas. So we're going from 6 moles of a gas to 7 moles of a gas. So that will give us a positive delta S, because we are increasing disorder. And we know from experience that combustion reactions get hot. They give off heat energy. When you just have a reaction, it's pretty easy to figure out delta H. Basically, if you mix 2 things together and they go to a higher temperature, it's exothermic, because it's giving off heat energy. And if you mix the 2 things together, or you do a reaction, the air around is getting colder, then it's going to be endothermic. So in this case, we know, because we've lit the Bunsen burners. The Bunsen burners are not propane, they're methane, but it's the same basic principle. If the propane is what's in your propane tank, most likely what's in your gas grill outside. If your parents barbecue or grill, or if you barbecue or grill, that's what's in there. When you buy it, it's interesting. It's under pressure, so it's in the liquid form. And then when you turn the valve, it sprays it out, and then it turns it to a gas because it goes to a lower pressure, which is 1 atm. So it turns into a gas, and then it mixes with oxygen and it burns it. But anyways, so this is going to be a negative delta H because it's exothermic. So when you have both a positive delta S and a negative delta H, oops, I forgot writing that. This is going to be a reaction that will always have a negative delta G, because if we have a negative delta H and a positive delta S, remember, because it's minus the temperature, so that's negative, this is negative. So when you add the two of them together, you always get a negative delta G. So this is going to be a negative delta G at all temperatures. And this is really important because when you have a combustion reaction, it's very difficult to stop it. So let's say, for example, you have a propane tank and like one of those huge ones that's on a train. This has happened many times. You have a train derailment and it catches fire. Well, you've got tons and tons of combustible material, and you've got oxygen from the air. So the only two ways to basically stop this reaction, because this is a very product favored reaction, is to either let the propane run out, so you use it all up, limiting reagent, right? Or you try to smother the oxygen to deny the reaction oxygen, which will stop the reaction from occurring. A lot of times they just don't even try to smother the oxygen with the large ones. They just wait until all of the flame is burnt out, because it's such a dangerous reaction to try to control. And the reason, again, why it is because it's really very product favorite. It has a very strong driving force to go towards the products. One of the other things, and I know I've said this a million times, but it's so critical, is that just because propane and oxygen react together, it does not mean that if I mix the two of them, they will instantly react. Because one of the other factors we have to consider, and this is really in the kinetics unit, but you have to at least be able to add it up, think about it here, is you have to put the activation, the energy of activation, into the reaction. So you need some sort of spark, something that will ignite it. Once you ignite it, this reaction will keep going, but you at least have to put that spark in to start the reaction. So in your grill at home, that's the little sparker, that little button that you push. Okay. So our next reaction here, and again, we're always coming back and thinking about our delta G equation, our as I like to call it, the goldfish equation or the Gibbs equation. Here we have melting ice. So we're going here from a solid to a liquid. So we are going more disordered because delta, so we'd have a positive delta S. Because a solid is the most ordered state, you're turning it into a liquid, so it's becoming more disordered. And you are having to put heat energy into this. It takes energy to weaken or break bonds. And in this case, the bond that we're weakening is the intermolecular force, which is the hydrogen bonding between the water molecules. We're not actually breaking any of the intramolecular bonds, but you're weakening the intermolecular force. So you have to put heat energy into it to weaken those bonds. So this would give us a positive delta H. So when we have a positive delta S and a positive delta H, that is going to give us so up here we've got a positive value and a positive delta S. But remember, when we have a positive delta S, the minus T delta S is really going to be negative altogether, right? Because you're minusing that. So this is a reaction that is going to favor high temperatures. And so negative delta G favors, so this will only have a negative delta G at higher temperatures. So in this case, we know what the temperature value is going to be, because obviously melting ice, if it's below zero, it's going to stay frozen, and above zero, it's going to melt. But each reaction will have its own temperature cutoff, and that's basically going to be where the sign of delta G is going to flip from negative to positive. So what you need is this factor here, the T delta S, to be more negative than the delta H is positive. So it's very important to think about it that way. So you need this factor here, right, to be a larger negative value than this is a positive value. And that's the only way you'll keep delta G negative. So as long as you have your temperature, right, up high, your T delta S, because the delta H will stay the same, delta S will stay constant. So what's changing is the temperature. So as long as you have a high temperature, you'll have a negative delta G. If you lower the temperature, right, then this factor keeps getting smaller and smaller and smaller until the minus here is going to be outweighed by the plus value here. And so then it'll flip your sign to a positive delta G, and this reaction will no longer happen on its own. It will stay reactant favored. Think about it, that makes sense with melting ice because it's going to happen at higher temperatures and not at lower temperatures. Well, what if we flip it over to freezing water? In this case, we're going towards a solid, so it's becoming more ordered. So it's going to have a negative delta S. A negative delta S means that it's more ordered, not more disordered, but more ordered. And we know that when bonds are formed, so here you have the formation of intermolecular forces or the strengthening of intermolecular forces, that it's going to be exothermic. And if, by the way, if you get confused about this, what you can do is you can figure out what it would be going from solid to liquid, just like we did in the last example. Here, we figured out that it was endothermic, right? So if you flip it, if you flip the reaction, then you also flip the delta H. So in this case, it's going to be exothermic, or release heat energy. And that's what your refrigerator does. Your refrigerator forces the liquid water to release heat energy. It basically sucks the energy out of it. And in doing that, that's what freezes the water in your freezer at home. So if both are negative, this is a reaction that is going to have a negative delta G at low temperatures. And doesn't that make sense? Because we know that water freezes at low temperatures. So again, you won't necessarily know for every reaction whether it's what the temperature cutoff is for low versus high temperatures, but in this case we know it would be 0 because we know that for water. And again, coming back up here, you've got a negative delta H, a negative but delta S, so it'd be minus a negative. So the whole factor here would be positive. So you need this negative delta H value to be more, to be a larger number, the negative number to be larger than the T delta S, because if not, then this over here will overtake this and force this to change to a positive G value, and then the reaction will not occur. So if we look at an example here, forming diamond. So going from graphite to diamond, diamond is the most ordered structure, crystalline solid. So that's going to be so you'd have to go to more ordered, so that'd be a negative delta S, okay? And this is going to be it's going to require heat energy, so a positive delta H. So if we think about this in terms of driving forces, neither one of these, you do not have a driving force here. If you do not have a driving force, this reaction will always have a positive delta G. So even if you increase the temperature, graphite will not transform into diamond. We've got a positive here, we've got minus and negative, so the whole factor is positive. There's no way for a positive and a positive to add up to give you a negative, so this will always be positive. This reaction requires incredible pressure. So not only do you need added heat energy to be put into it, but you need to add in pressure to form diamond. And that's why you see diamond mines 1,000 miles down, because it's all of that pressure from the earth that pushes on the carbon, whether it's in the graphite form or another form, to form diamond. By the way, in the previous examples, just to go back really quickly, we talked about this a little bit, but in our first example with a combustion reaction, both of these are considered driving forces, and that's why it's favored at all temps. If we look here, the positive delta S for the melting ice is the driving force. If we look here, the negative delta H is our driving force, and the one with the positive delta G, there is no driving force. Okay, thank you.